Welcome back to the deep dive. Are you ready to explore the amazing world of machine learning? It's basically teaching computers to learn from data without us having to program every single step. Pretty cool, right?
It is. And think about it, machine learning is already everywhere.
Yeah,
It's
exactly.
behind things like face recognition on your phone,
Uh-huh.
those personalized recommendations you get online,
Yeah.
and even self-driving
I
cars.
know. It's like having this invisible, super smart assistant,
hmm
right? Working behind the scenes, constantly learning and adapting to make our lives easier and more efficient. So to kick things off, our sources dive into three main types of machine learning. We've got supervised learning, unsupervised learning, and reinforcement learning. Let's start with supervised learning.
hmm
I feel like we're going to be teaching the computer like we would a student.
That's a great way to think about it. In supervised learning, we give the computer tons of labeled examples, almost like flashcards. You can think of it like teaching a child to recognize different animals. We show them pictures of cats, dogs, birds, and we label each one. The algorithm does something similar. It learns from this labeled data to predict outcomes for new data it hasn't seen before.
So, let's say we're trying to predict house prices.
Yeah.
We would give the algorithm a bunch of data points with the features of the house, like size, location, number of bedrooms, and of course the sale price.
Yeah.
And the algorithm would learn from this data to figure out the relationship between these features and the price,
Exactly.
so that it can predict the price of a new house based on its features.
Exactly. And that's a perfect example of one type of supervised learning called regression,
Okay.
where we predict a numerical value.
Go.
Another key area of supervised learning is classification.
Okay, so with classification, instead of predicting a number, we're trying to categorize data into different groups, right?
You got it. It's like sorting emails into spam, or not spam, or diagnosing a patient's illness based on their symptoms.
So for spam filtering, the algorithm would learn from a bunch of emails that are already labeled as spam or not spam,
Right.
and then use those patterns to classify new incoming emails.
Precisely. Now, to dive deeper into supervised learning, let's unpack some specific algorithms, starting with one of the most popular ones, linear regression.
Linear regression, it sounds like it involves straight lines. Am I on the right track?
You are. Imagine you have a scatter plot of data points, and you're trying to draw a straight line that best fits the data. That's what linear regression does. It finds the equation for that line, which represents the relationship between the input features and the output we're trying to predict.
So if we're predicting house prices based on size, linear regression would find the equation of a line that shows how price generally increases with size.
Exactly. Now, when we have multiple input features like size, number of bedrooms, and location, we use multiple linear regression.
Okay.
The equation gets a bit more complex, but the idea is the same, finding the best linear relationship to explain the data.
Okay, but what if the relationship between the variables isn't linear? Like, what if it's more like a curve?
That's where polynomial regression comes in. It's like
Right.
fitting a curved line to the data instead of a straight line, allowing us to model more complex relationships.
So if the price of a house increases rapidly at first as the size increases, but then levels off, polynomial regression could capture that curved relationship.
Right. Now, one important thing to keep in mind with all machine learning models is this balance between underfitting and overfitting.
Underfitting and overfitting. Can you break those down a bit more?
Absolutely. Underfitting is like trying to squeeze a square peg into a round hole.
Okay.
Your model is too simple to capture the patterns in the data.
Right.
Overfitting is like memorizing the answers to a test instead of actually understanding the concepts.
Yeah.
Your model performs well on the data it's already seen,
Okay.
but it fails miserably on new data.
So how do we avoid these pitfalls?
One way to avoid overfitting is to use a technique called regularization. Think of it like adding weights to a line to make it less wobbly and more generalizable.
Interesting. So it helps us find a simpler solution that performs better on unseen data.
Precisely. Now, another important concept is feature scaling.
Okay.
This ensures that all features contribute equally to the learning process.
Right.
Imagine a race where some runners have a head start just because their starting point is closer to the finish line. That's what it's like when features have different scales.
So feature scaling levels the playing field by adjusting the scales of different features. So does that involve like shrinking or stretching the values of features?
Exactly. There are different methods, but the goal is to ensure that no single feature dominates the learning process simply because its values are larger.
Makes sense. So we've covered linear regression, polynomial regression, underfitting, overfitting, regularization, and feature scaling. Are we ready to move on to other regression algorithms?
We are. Let's explore a completely different approach called K-nearest neighbors regression, or KNN for short.
K nearest neighbors, it sounds like we're analyzing a neighborhood.
That's a great way to visualize it. KNN predicts a value based on the average of its K nearest neighbors, the data points in the training set that are most similar to the new data point we're trying to predict.
Okay, so if we're predicting someone's income, we'd look at the incomes of, say, their 5 closest neighbors in the data set, those with similar age, education level, and years of experience,
Right.
and average those incomes to make a prediction.
Exactly. And the K value, the number of neighbors we consider, is a hyperparameter we can tune to find the best performing model.
Hyperparameter, that sounds important. Can you clarify what that means?
Sure. Think of hyperparameters like the settings on a camera. We adjust them to fine-tune the performance of the algorithm, just like we adjust the aperture or shutter speed to get the best picture.
This is getting really interesting. What other fascinating regression algorithms are waiting to be explored?
Let's step into the world of decision trees, specifically decision tree regressors. They're like flowcharts that guide us to a predicted value through a series of yes or no questions.
A flowchart for predictions, that sounds pretty intuitive. Can you give me an example?
Imagine predicting drug dosage effectiveness based on a patient's characteristics. Each decision in the tree is like asking a question: is the patient's age over 65? Or is their weight above a certain threshold? Each answer leads us down a different path, eventually reaching a leaf node, a final prediction for the dosage effectiveness.
So the tree is built by strategically choosing the best features to split the data at each decision point,
Exactly.
minimizing the errors in our predictions.
Exactly. And just like we prune branches of a tree to make it stronger, we can also prune a decision tree to prevent overfitting, making it more generalizable.
It's all about finding the right balance between complexity and simplicity. Are there any other algorithms that build on this idea of decision trees?
Absolutely. Let me introduce you to random forest regression, which is like having a team of decision trees working together.
So instead of relying on a single tree, we have a whole forest of them, combining their predictions to get a more accurate and robust result.
You got it. Each tree in the forest is trained on a slightly different random subset of the data,
Oh.
which helps reduce overfitting and makes the model more reliable.
It's like having a panel of experts giving their opinions, and then we take the average of their predictions.
That's a great analogy. Now, are you ready to delve into another powerful technique called support vector regression, or SVR for short?
Bring it on. The name sounds a bit intimidating, but I'm ready to tackle it.
SVR is all about finding the best line, or hyperplane in higher dimensions, to fit the data while allowing for some errors within a margin. Imagine trying to draw a line through a scatter plot of data points, but instead of aiming for a perfect fit, we allow for a bit of wiggle room.
So it's like creating a buffer zone around the line, making the model more robust to variations in the data.
Precisely. SVR focuses on maximizing this margin to improve generalization. And the data points closest to this margin, the ones that influence the line's position, those are the support vectors, the key players in this algorithm.
This is all incredibly fascinating. We've covered a lot of ground with regression algorithms,
Yeah.
from simple linear regression to these more advanced techniques. I'm eager to learn more about other types of machine learning, but I think this is a great place to pause for now.
You're right, we've covered a lot of material. In the next part of our deep dive, we'll explore the world of classification algorithms, so stay tuned for that. Welcome back to the deep dive. Ready to explore some more amazing algorithms?
Absolutely. Last time we took a journey through the world of regression algorithms,
Right.
learning how they can predict numerical values. What's on the agenda for today's exploration?
Today, we're switching gears to classification, a fascinating area of machine learning where we categorize data into different groups.
Okay, so instead of predicting a number, we're predicting a category or label. Like, is this email spam or not spam? Or is this image a cat or a dog?
Precisely. And we'll unpack some powerful algorithms that make this kind of classification possible. Let's start with one we've actually encountered before, logistic regression.
Wait a minute. Didn't we cover logistic regression in the regression episode? I'm a bit confused. How does it fit into classification?
That's a sharp observation. While it shares the name regression, logistic regression is actually a classification algorithm.
Okay.
It predicts the probability of something belonging to a certain category. Think of it like flipping a coin, but instead of just heads or tails, it tells you the percentage chance of getting heads.
Okay, I see. So instead of predicting a number directly, it predicts the likelihood of something being true or false. Yes or no, spam or not spam.
Exactly. Imagine an online ad. Logistic regression could analyze your browsing history and predict the probability of you clicking on the ad. This helps advertisers target their campaigns more effectively.
That's super smart. So what other classification algorithms are waiting to be explored?
Let's revisit our friend K-nearest neighbors, or KNN. Remember how it predicts a value based on the average of its K-nearest neighbors?
Yes. It's like analyzing a neighborhood and making predictions based on the characteristics of the closest houses.
Right. Well, in K&M classification, instead of averaging numerical values, we look at the majority class label among the K-nearest neighbors.
So if we're classifying fruits as apples or oranges, and we have a new fruit to classify, we look at its closest neighbors in the data set.
Right.
If the majority are apples, we predict our new fruit is also an apple.
Precisely. It's a simple but often effective approach.
I'm seeing a pattern here. Many of these algorithms can be used for both regression and classification. What other classification gems are hidden in our treasure chest of machine learning?
Let's delve into the world of probabilities with the naive Bayes algorithm. It's a powerful technique for calculating conditional probabilities, the probability of something happening given that something else has already occurred.
Conditional probabilities. That takes me back to statistics class. Can you give me a real-world example?
Imagine we're trying to predict whether a patient has the flu based on their symptoms. Naive Bayes looks at each symptom independently and calculates its contribution to the overall probability of having the flu.
So if a patient has a fever, cough, and a sore throat, the algorithm would consider each of these symptoms separately and combine their individual probabilities to estimate the overall likelihood of having the flu.
Exactly. It's like piecing together clues to solve a mystery. Each clue contributes to the overall probability of a suspect being guilty.
I'm starting to appreciate the power of probabilities in machine learning. What other classification wizards are ready to share their secrets?
Let's welcome back our flowchart friend, the decision tree, but this time in its classification form, a decision tree classifier.
I remember how decision tree regressors guide us through a series of yes or no questions to predict a numerical value.
Right.
Do decision tree classifiers work the same way?
They follow a similar structure, but instead of predicting a number, they predict a class label. Imagine identifying different animal species based on their features. Does it have feathers? Does it lay eggs? Does it have fur? Each answer leads us down a different path, eventually reaching a leaf node representing a specific animal.
So the tree is built by choosing the best features to split the data at each decision point,
Mm-hmm.
just like with regression trees.
Yes,
But this time we're trying to separate different classes instead of predicting a continuous value.
precisely. And we want each leaf node to be as pure as possible, ideally containing only instances of a single class. It's like sorting marbles into different jars based on their color.
This feels very intuitive. Are there any other algorithms that build on this tree-like structure?
There is. Let's bring back our ensemble powerhouse, the random forest. This time, in its classification form, a random forest classifier.
Ah, the wisdom of the crowd approach. So instead of relying on a single decision tree, we have a whole forest of them making predictions, and then we take a majority vote to determine the final classification.
Exactly. And just like with random forest regression, each tree is trained on a slightly different random subset of the data, which improves the model's robustness and generalization.
It's amazing how these algorithms can mimic real-world concepts like teamwork. What other powerful techniques are waiting to be explored?
Let's introduce Support Vector Machine, or SVM, an elegant algorithm for finding the optimal boundary between classes.
Optimal boundary, what exactly does that mean?
Imagine you have data points from two different classes scattered on a graph. SVM aims to find the best line, or hyperplane in higher dimensions, that separates these classes with the largest possible margin.
So instead of just drawing any line that separates the classes, it finds the line that maximizes the distance between the classes, creating a clear separation.
You got it. And those data points closest to this margin, the ones that influence its position, those are the support vectors, the key players in determining the optimal boundary.
It's like a strategic game of territorial control, maximizing the buffer zone between different territories.
That's a great analogy. And just like with support vector regression, we can use kernel functions to transform the data into higher dimensions if we need to draw more complex, nonlinear boundaries.
This is all incredibly insightful. We've explored a range of classification algorithms, each with its unique approach to categorizing data. Are we ready to move on to other exciting areas of machine learning?
We are. But before we do, let's bring back our sequential learning champion, XGBoost. Do you remember how it learns from its mistakes, iteratively refining its predictions?
Yes. It's like a student who learns from their wrong answers on practice tests. getting better and better with each attempt.
Precisely. Well, XGBoost also excels in classification tasks. It builds an ensemble of decision trees where each new tree is trained to correct the errors made by the previous trees.
So it's like having a team of detectives working on a case, with each detective building on the clues uncovered by the previous ones. That's amazing. Are we ready to switch gears now and dive into the world of unsupervised learning? Welcome back to the Deep Dive. I'm ready for more machine learning adventures. Last time we explored the world of classification algorithms,
Right.
learning how they can categorize data into different groups. What's next in our journey?
Get ready to explore the fascinating world of unsupervised learning. It's a bit like giving a computer a puzzle to solve without providing the picture on the box.
So instead of giving the algorithm labeled examples, we let it loose on unlabeled data and see what patterns it can uncover. That sounds like giving the computer a lot more freedom.
Exactly. In unsupervised learning, the algorithm's goal is to discover hidden structures, relationships, and patterns in the data without any specific instructions or predefined categories.
That's pretty amazing. What kind of tasks can we accomplish with unsupervised learning?
One major area is clustering, grouping similar data points together based on their inherent characteristics. Think of it like organizing your sock drawer, grouping socks by color, style, or length.
So in the world of data, we might cluster customers based on their purchasing behavior, group documents by topic, or even segment images based on visual similarities.
Precisely. Clustering helps us uncover hidden structures in data, revealing groups and relationships that might not be immediately apparent. Let's dive into a popular clustering algorithm called K-means.
K-means. Does the K stand for something?
It does. K represents the number of clusters we want to create. Imagine you're dividing a city into different districts based on the locations of shopping malls.
Yep.
Each data point represents a resident, and we want to assign them to the nearest shopping district.
So K-means would find K cluster centers, representing the locations of those shopping malls, and then assign each resident to the cluster whose center is closest to their home.
That's a great analogy. It's an iterative process. The algorithm starts with random cluster centers and then refines them with each iteration, moving them closer and closer to the true centers of the clusters.
So it's like finding the ideal locations for those shopping malls to minimize the distance residents have to travel for shopping. But how do we determine the optimal number of clusters? The K value? Do we just guess?
We can use techniques like the elbow method to guide our choice.
Oh.
We plot the distortion, a measure of how spread out the data is within each cluster, against different K values. The elbow point on this plot suggests a good balance between the number of clusters and the amount of distortion.
It's like finding the sweet spot where adding more clusters doesn't significantly improve the separation of the data. K-means sounds pretty intuitive. What other clustering techniques are out there?
Let's explore hierarchical clustering.
Okay.
Instead of finding a fixed number of clusters, it builds a tree-like structure, a dendrogram, that shows how data points are related to each other.
Dendrogram. It sounds like a family tree for data points.
You're exactly right. Imagine grouping students in a class based on their similarities.
Okay.
We might start by grouping students who sit near each other, then merge those groups based on shared interests and so on, building this hierarchy of relationships.
So the dendrogram shows us the hierarchy of clusters, from individual data points all the way up to a single cluster containing all the data. And we can then decide how many clusters we want by cutting the dendrogram at different levels.
Precisely. It's like pruning a tree to create separate branches. Now, let's shift gears and explore a different task in unsupervised learning: anomaly detection.
Anomaly detection. That sounds intriguing. Is it about finding those data points that are out of the ordinary, the ones that don't quite fit in?
You got it. Anomaly detection is all about identifying those data points that deviate significantly from the norm, often indicating unusual or suspicious events.
So it's like spotting a mismatched sock in a drawer, or finding a counterfeit bill among a stack of genuine ones. What are some real-world applications of this?
Anomaly detection is used in various fields. For instance, in finance, it's used to detect fraudulent transactions.
Makes sense.
In manufacturing, it can help identify faulty equipment. And in cybersecurity, it can flag unusual network activity that might indicate a security breach.
That's incredible. But how do we actually identify these anomalies? Do they have some kind of secret code?
One common approach is to assume that our data follows a normal distribution, the bell curve we often see in statistics. Anomalies are those data points that fall far away from the mean of this distribution, the outliers on the tails of the bell curve.
So they're the data points that have a low probability of occurring under the assumed distribution, making them stand out as unusual or suspicious. It's like finding those students who score way above or way below the average on an exam.
That's a great way to put it. Anomaly detection is particularly useful when we have limited labeled data for anomalies or when the types of anomalies we're looking for are constantly changing.
This is all incredibly insightful. We've covered supervised learning,
Yeah.
unsupervised learning, and so many fascinating algorithms. Is there anything else we need to explore in the world of machine learning?
There's one more exciting area we should delve into: recommendation systems. Those personalized suggestion engines that seem to know our tastes better than we do.
Oh, yes. Those recommendations that pop up when you're browsing online, suggesting products you might like or movies you might enjoy, they can be eerily accurate.
Recommendation systems often combine collaborative filtering and content-based filtering to create those personalized suggestions.
Okay, I'm intrigued. Let's break it down. What's the story behind collaborative filtering?
Collaborative filtering is based on the idea that people with similar tastes tend to like similar things. Think of it like asking your friends for movie recommendations.
Mm-hmm.
If they have similar taste in movies, you're likely to enjoy their suggestions.
So if I love sci-fi movies and my friend also loves sci-fi movies and they recommend a new sci-fi film I haven't seen, chances are I'll enjoy it too.
Exactly. Recommendation systems analyze vast amounts of data on user preferences, ratings, reviews, purchases, watch history. Right.
To find those taste-alike groups and recommend items based on what similar users have enjoyed.
That's really clever. And what about content-based filtering? Does it involve some kind of deep analysis of the content itself?
You're right on the mark. Content-based filtering focuses on the attributes or features of the items themselves, as well as the user's past preferences.
Okay.
It's like recommending books based on the genres, authors, or themes that a user has enjoyed in the past.
So if I've read and enjoyed several mystery novels by a particular author, a content-based system might recommend other books by that author or books with similar themes or settings.
Exactly. To make these recommendations, algorithms use feature vectors, numerical representations that capture the key characteristics of each item and user.
So a mystery novel might have a feature vector that includes high values for mystery, suspense, and detective, while my user profile might have high values for those same features if I'm a big fan of mysteries. Precisely. And we can find similar items or match users with items they're likely to enjoy by calculating the distance or similarity between these feature vectors.
It's like finding books that are close together on a bookshelf organized by genre. But how do we create these feature vectors in the first place? Do we have to manually analyze every item?
That would be quite a task. Luckily, we can use machine learning algorithms, such as neural networks, to automatically extract these features from data like text, images, or audio.
Neural networks, those brain-inspired algorithms, they sound incredibly powerful.
They are. Neural networks can be trained to recognize patterns and extract meaningful features from vast amounts of data. In the context of recommendations, they can analyze things like movie descriptions or book summaries to automatically identify genres, themes, and styles.
So neural networks help automate the process of understanding and categorizing content, making it possible to create those personalized recommendation lists that feel like they're reading our minds.
Exactly. Neural networks and other machine learning techniques are constantly evolving, making recommendation systems even more sophisticated and accurate.
This has been an incredible journey. We've explored supervised learning, unsupervised learning, and even touched upon the fascinating world of recommendation systems. It feels like we've covered the entire spectrum of machine learning.
We've certainly explored a wide range of algorithms and their applications, but this is just the beginning. The field of machine learning is vast and constantly evolving.
It's both exciting and a bit overwhelming to think about all the possibilities. But I feel like we've gained a solid foundation in the core concepts of machine learning.
We've learned how these algorithms can learn from data to make predictions, classify information, discover patterns, spot anomalies, and even recommend things we might enjoy.
It's truly amazing to see how these algorithms are transforming our world, from personalized experiences to groundbreaking advancements in healthcare, finance, and technology.
As we wrap up our deep dive, we encourage you to keep exploring this fascinating field. There's always something new to learn and discover. Who knows what incredible applications of machine learning await us in the future?
Until next time, fellow knowledge seekers, stay curious and keep exploring.